Thank you for the kind invitation. I'm very happy to be at this meeting. And today I'll tell you about topological currents and twist angle disorder in magic angle graphene and some unconventional Landau levels in these structures. So the picture that you see here is actually an image of the Landau levels in magic angle graphene as a function of position and the carrier density. And this novel imaging technique was developed by Aviram Uri and Samir Grover, and we thank our funding agencies. So let me start from our experimental technique, which is squid on tip. The way we fabricate the squids is that we can take a quartz tube of about 1 millimeter diameter and pull it into a sharp pipette, a few tens of nanometers. And then we use one of our favorite superconductors, usually lead or indium, or more recently molybdenum. And we do 3 depositions. In the first deposition, we coat one side of the pipette. Then in the second deposition, we coat the other side. And in the third deposition, we coat the apex of the ring at the apex. And as a result, we have 2 superconducting leads connected to a ring. In the regions where the leads overlap the ring, we have stronger superconductivity. And these nanobridges that are formed between the leads are actually the weak links that form a squid loop. So as a result, we have a very small squid residing on a sharp needle. This is how it looks in a SEM image. So this is one lead lead, this is the other. This is the gap between them, and you can hardly see the hole at the apex. These devices can be as small as 40 nanometers. They operate in magnetic fields of about a Tesla. Recently, we developed molybdenum tips that can work up to 5 Tesla. They have extremely low flux noise of about 50 nanophi per square root hertz, which translates into a spin noise of about 1/3 Bohr magneton per square root hertz, which means that we have enough sensitivity to image the magnetic field of a single electron spin. Also recently, we have shown that these devices can be extremely sensitive thermometers, allowing thermal imaging with a sensitivity of a microkelvin per square root hertz in order to study dissipation in quantum systems. Unfortunately, I will not have time to describe thermal imaging today. So we'll focus only on magnetic imaging. So in order not to crash into the sample, we attach the squid on tip to a quartz tuning fork, as you can see here in the SEM image. And we follow and we trace the resonant frequency of the tuning fork, and then when tip approaches the sample, we can sense it like in an atomic force microscope, which allows us to scan the surface with few tens of nanometers above the surface. We also take advantage of the fact that the tip resides on the quartz tuning fork, and when we oscillate the tuning fork, we also oscillate the tip parallel to the surface with an amplitude of few nanometers. And as you will see, it can come handy for several applications. So in the first part, I will describe imaging equilibrium currents in the quantum Hall edge states in graphene. In the monolayer graphene, this was carried out in collaboration with Jürgen Smet and Young-Woo Kim from Max Planck Institute in Stuttgart and with Cyprian Lewandowski at MIT. So when we think of quantum Hall effect, we usually describe in terms of Landau levels, which are full up to some Fermi level and empty above it. So a full Landau level in the bulk, the electrons form orbitals, closed orbitals, which are considered as an insulating state, a bulk. And along the edges, we have chiral edge states. These are the skipping orbits that we usually think of in terms of quantum Hall. And they cause current to flow in one direction on one side and in opposite direction on the other side. So these are the 2 edge states of the quantum Hall, which result in quantum conductance. And there were numerous works aimed at imaging these edge states. using electrostatic potential imaging and microwaves and so on. So people have seen these edge states, but the actual current that flows in these edge states has never been imaged directly. So for this, we use our squid on tip. So this is a schematic setup. This is our graphene encapsulated in bottom and top HBN. And let's assume that we, yes, and all our measurements at 300 millikelvin, typically in magnetic field of about 1 Tesla. And we have a backgate with which we can control the carrier density in graphene. So let's assume we're in this situation that where we have just one edge state, so one Landau level crossing the Fermi level, and therefore it is expected to have one channel of current flowing. It should be a narrow channel. So if we take a cross section in this in here along X, we expect a narrow strip of current. This is current density, and of course this current will create magnetic field through Biot-Savart law. So this is the Biot-Savart calculated for this strip of current, taking into account the height at which we scan and the diameter of our tip. So you see, and we measure only out of plane component of the magnetic field, BZ. So you see on the right-hand side the positive field, and on the left-hand side of the strip a negative field. And of course, one can take this, if you map out this field in the entire space, in principle, you can invert it back into the current. It's a non-trivial procedure which causes instabilities and noise. But using the fact that our tip resides on a tuning fork, we can take advantage of this and cause it to oscillate, let's say in X direction. And if we measure the magnetic field at this oscillation frequency, we actually measure the derivative, dBz dx, if the amplitude of oscillation is small. And one can show that the derivative reproduces quite accurately the original current. So the derivative of Biot-Savart actually is very close to the original current. And so this peak in current is visible here. And it is broadened just by the height of the scanning and the diameter of our tip. So if we measure this BZAC, this is what we are supposed to see. So this allows us direct imaging of the current. So essentially, by taking the derivative of the Biot-Savart in real time, we image directly the current. That's how you should think about it. And I emphasize that our graphene is grounded and there are no external applied currents. So all the currents that I will be showing you are equilibrium currents flowing in the ground state in the quantum Hall state with no externally applied current. So now we will use this in order to study the currents flowing in the quantum Hall state in monolayer graphene. So this is our edge. We make this edge artificially by having a split gate. So here we have a back gate, and we tune the carrier concentration here near charge neutrality. And here we have another back gate where we can tune the carrier concentration to any value that we want. And then what we'll do, we'll just change the Fermi level in this part of the sample and study the resulting currents. So this is the schematic Landau levels, the density of states, and the corresponding filling factor, 2, 6, 10, and so on in graphene. So let's start from a situation where we are close to charge neutrality, so filling factor 0.7. We see no currents except those related to disorder, which I will not describe today. So now we'll increase this to fill the first Landau level up to filling factor of 2. So this is, we increase the filling factor and you see currents appearing. And in particular, we observe a current flowing downstream as we expect. So again, this is the units here are actually current density. This is the spatial resolution. So this is the direct imaging of the edge state current. So right now we're in this situation. We have one edge state. We expect one downstream current. These are the skipping orbits. And indeed, this is what we observe. So we are now celebrating 40 years of quantum Hall. So this is the first time actually these equilibrium currents can be imaged directly. So far it fits our expectation. Now let's go to the next Landau level. So we'll fill up now to 6 or so. So as we increase, we see this edge state moving towards the edge as we expect, becoming narrower. But surprisingly, now we see a current flowing in the opposite direction, following by another current flowing downstream. So right now we are slightly above a filling factor 6. So it means that schematically, this is the situation. We have 2 edge states, and therefore we expect 2 downstream currents. Indeed, we see these 2 downstream currents, but very surprisingly, we see current flowing in the opposite direction. So black is opposite direction of current. And we will call this non-topological current. These are the topological skipping orbits currents that we expect. So let's go to the next Landau level. So now we'll go to 10. So these edge states get closer to the edge, they start overlapping, but then again, we see an opposite current followed by another topological current. So now the situation is that we have 3 Landau levels, we expect 3 downstream currents. So we have 1, 2, 3, but surprisingly between them, we have a non-topological current flowing in the opposite direction, and you can see that it's of comparable amplitude as the currents that flow downstream. And if we continue further on, it repeats itself. So again, we now have another non-topological upstream current following by another one downstream. So this is not what we expected. So the conclusion is that the incompressible strips, so these are incompressible regions, they carry downstream topological currents that we usually think of. But surprisingly, compressible strips between them carry opposite current upstream, which we will refer to as non-topological current. It turns out that this has been predicted long time ago theoretically by Geller and Vinale, but since nobody has ever seen that, this was long forgotten and ignored. Unfortunately, I don't have time to describe in more details the physics behind it, and I want to move on to magic angle graphene now that we know what to expect in regular quantum Hall state. So magic angle graphene, this was done in collaboration with MIT team of Pablo, Johan, and Daniel. Our setup is very similar. So now we have a twisted bilayer graphene encapsulated between bottom and top HBN, where similarly at 300 millikelvin, about 1 Tesla magnetic field. And again, the magic angle graphene is grounded. There are no external currents. So whatever we will show is equilibrium currents flowing in the ground state in the magic angle graphene. So if we look at this sample, this is what we see. So these are the edges of the magic angle graphene in black. So it's a whole bar, part of the whole bar. And what surprisingly we see incompressible downstream currents. This is a topological current, this red. And dark blue are the non-topological currents in the compressible regions flowing in the opposite direction. And the first striking observation here is that the quantum Hall edge states appear in the bulk of the sample rather than along the edges, as we saw in a monolayer graphene. Moreover, if we now change the backgate, we see these edge states moving around, but they never reach the edges and they never flow parallel to the edges as our usual thinking of quantum Hall state is. So as we will see later, in magic angle graphene, there is a gradient of twist angle, and this gradient causes formation of Landau levels in the bulk along the gradient, in which topological current flows in the incompressible strips and non-topological current flows in opposite direction in the compressible strips. So, and in this case, so previously we have used the tuning fork to oscillate the tip in order to image the current. Instead of oscillating the tip, we can oscillate also the edge states themselves by applying an AC voltage to the backgate, and we'll get a very similar result, which will be direct imaging of these currents flowing in the incompressible and compressible regions, and the signal that we measure is proportional to this current. And again, I remind you that these are equilibrium currents. Just I'll skip the description of the magic angle graphene physics following the beautiful presentation of Dima, and I'll just mention that what one has to think of this band structure when we're near magic angle, that we have flat bands separated by band gaps to dispersive bands, so this is the N dispersive band, and this is the P dispersive band, and it takes 4 electrons to fill the flat band, or 4 holes to empty the flat band. And since 4 electrons or 4 holes per Moiré unit cell, and since the size of a Moiré unit cell depends on the angle, so if we change the angle, we shrink or expand this Moiré unit cell. So there is a direct relation between the Curie concentration required for filling up the bands, namely 4 electrons per Moiré unit cell, and the twist angle. And if one knows NS, measures NS, you can extract theta and vice versa. So we will be using this in order to study the twist angle disorder. So now let me flip this band structure and start from the conventional transport measurements. So these are the global RXX measurement in one of the samples. So, and this is the filling factor in units of 4 electrons per Moiré unit cell. So this would be the full flat band would be here, and the fully emptied flat band would be here. And these are the dispersive bands. So what one sees is, first of all, superconductivity. For example, here at filling factor of -2 plus epsilon. And as Dima and Fetef have shown, this superconductivity can appear at various positions at various filling factors. In this particular sample, this is where we have the superconductivity. And you see Landau fans at high magnetic fields that emerge either from charge neutrality, and some of them from filling factor 1. This is what Dima mentioned, that this looks very similar to what he mentioned in the context of topological bands. This is filling factor 2, and so on. Some you see more pronouncedly, some less, and you barely see Landau fans in the dispersive bands. And if we take a line cut through this transport data, global transport data at 1 Tesla, this is what you see. So this is the same data along this line, RXX on logarithmic scale, various carrier density. So you barely see quantum oscillations at 1 Tesla near charge neutrality, and you don't see essentially any of the quantum oscillations at other filling factors at this low field. For this, you have to go, in order to see them properly, you have to go to much higher fields. But now we can do the same thing essentially with our tip. So this is for comparison. The local measurements of BZAC, I remind you, this is proportional to the local current flowing under the tip at some random position in the sample at the same magnetic field. And what you see is very sharp peaks appearing at various filling factors. So the height of the peak is proportional to the gap energy of the Landau level gap energy, and the distance between the peak directly gives us the degeneracy. So for example, the 0th Landau level is 4-fold degenerate. So Adi was asking this question. So let's say at 1 Tesla, we see very well developed Landau levels. Perhaps some of them are Chern insulators, but but to us they all appear essentially the same. And this one is 8-fold degenerate. So you jump from -4 to 4. And all the rest are 4-fold degenerate, at least at these low fields. At high fields, you see that some of the degeneracy is lifted. The Landau levels that are formed above filling factor 2 are 2-fold degenerate. Those that globally you don't see them at all, but locally you see them nicely, they're 1-fold degenerate. And the dispersive bands are usually 4-fold degenerate, as you see here, and occasionally we see an 8-fold Landau level between 4-fold Landau levels. So what one clearly sees is that even though globally you don't see clearly resolved Landau levels, locally the quantum hole is fully developed. You see very sharp incompressible regions separated by compressible regions. So now let's focus only on these dispersive bands. So these are the Landau levels in the dispersive bands, and as I said, they are 4-fold degenerate, so we know exactly the distance between them. But now if we measure the distance between this Landau level and this Landau level, the distance between them in units of K-ray concentration will be all the degeneracy of the Landau levels. So 12 nu equals 12 here and 12 here, so this is 24, plus 2ns, namely we have to fill all the flat band before we start filling the Landau levels in the dispersive bands. So if we know this distance in units of K-ray density between these peaks, we know ns. We just extract this ns. And since ns is related to theta, we can get the local theta at the position of the tip. And the remarkable thing here is that these peaks are extremely sharp. For us, they just have a width. We can determine them to a single measurement point, which translates in backgate to about 1 millivolt. The distance between these peaks is about 20 volts as compared to 1 millivolt. So this gives us a fantastic accuracy in determining ns, which translates into a relative accuracy in theta of just 0.2 millidegrees. And this is with spatial resolution of about 50 nanometers. In the following, I'll show you 2D maps of theta, which we take with larger steps. And therefore, we can attain 2D maps of theta with an accuracy of 1 millidegree. So this was a measurement at a single point in a sample. But now we can take a line scan. Instead of looking at one point, we can look as a function of position along this yellow line. And this is what we see. So this is the position along this line. And this is the backgate and the corresponding filling factor, let's say at this point. So this 2D image is equivalent to this one. So whenever an incompressible strip is under our tip, we get a sharp peak. So these are the peaks. But now we see that the peaks, the position of the incompressible strips, is position dependent. So we can use the same trick of counting the Landau level. We can determine the local ns. So this is the local ns as a function of position. So the distance between these two lines is twice ns. So here the distance is smaller, namely we have smaller ns here and larger ns here. And we can just read out ns directly from this plot. And this is what is given here. So this is ns as a function of position over about 3 microns. And we see that ns varies by about 10%. So this is ns disorder. And we can directly from this extract the local twist angle since it's proportional to the square root of ns. So if ns changes by 10%, theta changes here by 5%, from about 1.12 to about 1.17 over 3 microns. So this is twist angle disorder along this particular line in this image. So again, the distance between these two lines is determined by theta. So the difference between this and this gives us a theta. But also, if we have charge disorder, the charge disorder will shift these lines in the same direction. So the difference between these two lines, so this is the difference gives us the theta, and the sum of these two lines, the average if you want, will give us charge disorder. So we can also extract from this a charge disorder along this line as a function of position. And we see that it's on the order of few times 10 to the 10 compared to NS, which is a few times 10 to the 11, close to 10 to the 12. So it's clearly that the twist angle disorder is the dominant origin of disorder here. And you can even see it by your bare eye that these two lines look almost antisymmetric, which is the result of twist angle disorder. So now that we know the NS and the charge neutrality, we can plot all the other integer filling factors. And what becomes clear here is that the Landau levels in the dispersive bands are very robust. The Landau levels near charge neutrality are also quite robust, but the Landau levels emerging from these strongly correlated states at these integer fillings are very sensitive to twist angle disorder, and they appear only in very few places in space. So the correlated states are very fragile with respect to twist angle disorder, which is the first conclusion here. So we have seen what happens at one point along a line, but now we can go to full two-dimensional imaging of the sample. So now we will take this entire area, and we will take a movie of this position of these Landau levels in the sample. And this is how it looks. So we change the backgate. This is X and Y. And what we see is Landau levels appearing all over the place, moving around with very weird dynamics. So again, I remind you, the red are incompressible strips and the dark blue are compressible strips. So it's very hard to make sense of this. So we will just make a three-dimensional structure of the Landau levels, namely tomography. So this is the tomography of the Landau levels as a function of position and the carrier density, backgate, or energy if you want. And what you find, so in this three-dimensional space, the Landau levels form a manifold. Ideally, this manifold should be flat and only towards the edges should go up. But what you see that this manifold does crazy things inside the sample. And moreover, there are regions which show no Landau levels at all. And also here you can see, so for example, these Landau levels are fourfold degenerate. Here is one Landau level which is eightfold degenerate. And again, fourfold degeneracy here. So following the same procedure of extracting NS from Landau levels, we can now make a two-dimensional map of the twist angle, and this is the result. So this is the landscape of the twist angle from spanning a region from 105 to 1.18 in this particular sample, forming a very complex landscape. And moreover, there are quite extensive regions in the sample that show no Landau levels at all, namely no magic angle physics. If we compare our map to the AFM image, we find that the bubbles that Dima has mentioned in his talk, these are the locations. These dark contours are these bubbles that we see. So the bubbles kill the magic angle physics entirely within them and within about half a micron around them. This is the scale of 1 micron. But in addition, we have quite extensive areas that we do not see any particular features in the AFM image, but still they show no magic angle physics, either because the twist angle is very different from the magic angle or that a very high disorder. But now you have to realize that this map, this topography of twist angle is essentially the energy landscape for the Landau levels. Since the Landau levels have to follow the bottom of the band, and the twist angle determines the bottom of the band, of the dispersive band. So dark here, the lowest twist angle corresponds to the lowest energy for the Landau levels, and the bright will be the highest energy. So for example, if we think how the Landau levels would evolve, they should start from the lowest potential and then climb this landscape, forming some arcs here. In this region, if we look at this region, for example, we have two minima, and then we have a saddle point here and another. So now we can look at this movie again and try to make sense of it. So let's first look at this part where we have a minimum, and we expect the Landau levels to climb up this landscape. So you will see Landau levels forming here and forming these arcs, which are equipotential lines, which are equitheta lines for the Landau levels, and you see how they climb and new ones are formed at the bottom and expand upwards. But the amazing thing is that we usually think of Landau levels as that they must close some contour. Landau levels are topological objects, so they cannot just start and end in the middle of the sample. Remarkably, however, this is what we see. So this arc is an incompressible region, which is a Landau level crossing the Fermi energy, the Fermi level, and it just starts somewhere and ends somewhere at these regions which do not have magic angle physics, which is very unusual. Now let's look at this region. So we expect Landau levels to form at this minimum, and this minimum climb to the saddle point, merge and split, and climb these gradients. So let's look in this region. So this is what we will see: Landau levels forming here on one side, and another one's here, and they come and merge in the middle. Here another one merges, the third one comes in, merges, splits, and flows in the two opposite directions. So having understood the map of the twist angle, the disorder, we can understand the dynamics of these Landau levels as a function of backgate. But now we can look at some statistics of the twist angle disorder. So this is the histogram of the twist angle in this particular sample. So it spans from 105 to 118 with rather uniform distribution. And here's another sample which had no bubbles in it, another whole bar. And this is the corresponding twist angle map of this sample. It has a similar distribution, but instead of one peak, it shows two peaks in the distribution. And we can now compare to the average theta that one extracts from transport data. So this sample had a global twist angle of about 1.15, which corresponds well to the distribution that we see. This sample showed a global twist angle of 106, which corresponds to the upper part of the distribution. And if one looks at the twist angle map, it becomes obvious why it is the case, because this is our whole bar. We drive current from here to here and measure voltage between these two contacts. And therefore, we'll probe mainly the central part of the whole bar, which you can clearly see that has a higher twist angle. This is this distribution, whereas the lower part of the distribution belongs to these more remote regions, which are hardly probed by transport measurements. And moreover, since we can extract the twist angle with very high precision, we can just numerically calculate the gradient of this twist angle. So naively, it looks quite smooth, but once you look at the gradient, so this is the absolute value of the gradient in degrees per micron, you see that actually the twist angle disorder forms patches, a mosaic, where in regions where the disorder, the twist angle gradient or the twist angle changes smoothly, but separated by what we believe are stacking folds, across which the twist angle changes abruptly between these neighboring parts of mosaic structure, if you want. If we look at this sample, we get a very similar structure. Again, rather uniform areas with fraction of micron in diameter, separated by a network of stacking faults across which the twist angle changes quite abruptly. We can also extract the charge disorder, but I will not have time to describe it. So now knowing this landscape of the twist angle, we can look back on the global transport measurements and compare these two samples. So this sample, as you remember, this was the first one that I showed, for example, showed a very fully developed superconductivity. Namely, in this region, we have zero resistance. We have very sharp peaks in the IDVs. And one can understand why. Because here we have a fully connected region of magic angle physics between the voltage contacts. If we look at this sample, in contrast, we saw some suppression, but it goes down to a couple of hundred ohms, maybe also here. But obviously, once you know the map of the twist angle, and assuming the twist angle has to follow some specific theta or some range of thetas, there is no percolation of superconductivity between these two voltage contacts, and therefore the resistance will never go to zero. Also, you can see that this sample pronounced much more clear Landau fans as this one, and in particular here we see some Landau fans coming from the correlated states, whereas here we hardly see any, which again emphasizes that the correlated states are much more fragile, much more sensitive to twist angle disorder. So let me just come to my last slide, and to give you some insight, what is the implications or importance of twist angle disorder, which is really a new type of disorder, very different from types of disorders that we've been used to in the past. So the first is that it is band structure disorder. Namely, if we have two regions, if magic angle graphene with different twist angle, the band structure will be different in these two regions. Obviously, this will cause also effective mass disorder. So an electron that goes through the sample will change its effective mass as it passes through. The gradients in twist angle break the local symmetry. So we have symmetry broken disorder, and moreover, the direction of the twist angle gradient determines the direction in which the symmetry, the local symmetry, is broken. So the symmetry is different in different places, and also its orientation is different. But it's more than that. So let's take two regions. For example, the right-hand side has a slightly larger twist angle than the left-hand side. So this means that here we will have a larger bandwidth of the flat band, and also a higher density of states. So let's start from a situation where our backgate is zero, namely the Landau level, the Fermi level is at charge neutrality, with full states below and empty states above. And in this situation, the behavior in these two sides, besides of course all these points, are rather similar. However, now that we increase the backgate, we start filling up the density of states. So for example, we apply some voltage so that the level, so we fill the states here up to some chemical potential, determined by the total carrier density induced this part by the applied voltage and the capacitance. In this region of the sample, we'll have the same voltage and the same capacitance. Namely, we have to fill up this region to the same density of carriers, which will translate into a different chemical potential. So since the density of states here is larger, it means that the chemical potential here will be lower. But the Fermi level has to be flat. And for example, let's define it as 0 if we ground the magic angle graphene, which means that the changes in the chemical potential must be compensated by changes in the electrical potential. So now we have a situation where we have electrical potential different in different places, which means that we have electric field. The gradient of this electric potential, electrostatic potential, is equal to the gradient in the chemical potential, which means that now we have electric fields built in the system. So this is a very unusual situation. We are in a metallic state, and we are used to think that metal must screen electric fields, namely there should be no electric fields in a metallic state. Here, in contrast, we have a system that spontaneously generates electric fields that cannot be screened in a metallic state. So this means that twist angle disorder will cause large unscreened electric fields, and moreover, these electric fields will be gate tunable. As I mentioned, if we're at charge neutrality, there will be no electric fields, and they will grow as we apply back gate voltage. So this is numerical calculation taking into account DFT calculations of the band structure. And for example, let's take a situation where the twist angle changes from 1.1 to 1.15 over 2 microns, comparable to our experimental situation. So this electrostatic potential will be position dependent, and this is how it will look. And this is a resulting electric field, which is very significant. It's on the order of a kilovolt per meter, due to this effect, due to differences in the density of states in the different regions. We can also calculate the carrier density, and you see that the carrier density changes by 10 to the 8, compared to 10 to the 12 carriers that we have here, which means essentially the carrier density is uniform, determined by the backgate, but we have large internal electric fields created in this state. These electric fields will have a huge effect in when we apply magnetic field. So this is a calculation for 1.2 Tesla magnetic field. So since we have calculated the band structure, we can calculate the Landau levels. And in this case, the Landau levels will be tilted because the bottom of the band, of the dispersive band in this particular case, will be position dependent. And as a result, we will form compressible and incompressible strips. And there will be a sharp step in the chemical potential across the incompressible strips. And there will be a corresponding step in the electrostatic potential. So this explains how come we see Landau levels in the bulk of the sample. So this is the reason for the quantum Hall edge states being present in the sample. But this change in the chemical potential will result in very large electric field. So now we have electric fields formed in the incompressible regions of the order of 100 kilovolts per meter. And of course, these electric fields times sigma xy will be our topological current. And you see that we will get very sharp peaks in the topological currents in the incompressible strips on the order of a few tens of nanometers. So these are exactly the peaks that we see in our data that I've shown you in the beginning. So every time such incompressible strip passes under our tip, we see a large peak. And again, the carrier density is rather uniform in the sample. So yes, and of course also, since the dispersive bands actually the two degenerate bands, we've slightly shifted in K-space and slightly different mass. So this will result in occasional crossing of the Landau levels. So this is a situation, for example, that we will have four 4-fold degenerate Landau levels, followed by 1/8-fold degenerate Landau level, and again 4-fold, exactly as we see in the experiment. So the summary of this is that twist angle disorder is really a very different and in many senses counterintuitive type of disorder that we have to study more extensively. So far we do not know much about it. In particular, the symmetry breaking effects of this disorder and the presence of large in-plane electric fields. So let me thank people who did all this work. So at Weizmann, all the scanning squid experiments were carried out by Aviram Uri and Samir Grover. The squid on tips were fabricated by Kosik Bagani and Yuri Masuedov. Nadav Auerbach carried out some numerical calculations, and Elal Achman built the original microscope that we've been using. The MIT team, with excellent samples that we received from them. The band structure calculations come from Mikito Koshino, Pyung-Young Moon, and Alex Cross. The monolayer graphene study that I've showed you was in collaboration with Jürgen Smet. The HBN comes from NIMS, as usual, and our superconducting electronics is in collaboration with Martin Huber. So let me just leave you with these movies, and I thank you for your attention.